Okay, so number 8 says, know how the properties of liquids vary from those of gases, including viscosity and surface tension, because those aren't ones that apply to gases. But before we talk about what each of those properties are, and we've talked about density, compression, diffusion, we've talked about the first 3 already, but what 3 things are going to affect these properties? Pressure on the substance. Yeah, ultimately they're all affecting the motion. So what else would affect the motion besides the pressure, the energy or temperature, the intermolecular force? So if you have a liquid and a gas at the same temperature, the energy is the same. What can you assume about the density of the liquid compared to a gas? I don't think I can think of a certain case where the liquid of the density, I mean, the density of a liquid is less than that of a gas, right? Theoretically, it could be, I suppose. I mean, it'd be different substances. But the density of a liquid should be more because what makes a liquid a liquid? The particles are close together. In fact, they're close enough together to maintain their volume, whereas gases don't have any set volume. So density is going to be higher than in a gas, but less than a solid, except of course water, the odd one. Because liquids have particles close enough to stay together in a, we call it a defined volume. Okay, so in the case of density, it's the intermolecular force that's creating the liquid at room temperature. So if you have a gas and you want to make it a liquid, like liquid nitrogen, guess what they do to create liquid nitrogen? They put a whole bunch of pressure on it. That's how they liquefy oxygen and nitrogen to make it easier to transport. It's all about the pressure. Because you can't change the intermolecular force. They're going to be nonpolar. You could make it really cold, but they have to drive it around in this big, super cold refrigerator truck. So pressure is the easy way to liquefy them. How about compression and expansion? How does the compression and expansion of liquids compare to gases? Higher, lower, same? Yeah, it's much, much lower because they're already so close together, right? There's not much, so compression is much less since the particles are already close. Why is expansion less? I mean, if the particles are close, doesn't it seem like, well, gee, they must expand then to get away? Because the intermolecular forces have taken over here. Okay, so if you're going to expand it, you have to put enough energy to hit that boiling point. Okay, liquids will expand a little bit as they heat up to their boiling point, but the big expansion comes when they change to a gas. On average, a drop of water takes up about 1,000 times as much space as a gas. That's how much they expand. How about diffusion and effusion? Is it going to be easier for liquids to spread through each other? So this is like your creamer in your coffee. This is like going through a crowded hallway. Is it easier to get through a crowded hallway or easier to get through the empty hallway? The empty hallway. The gas is the empty hallway. your liquid is your crowded hallway. So it still happens. Slower than gases. So actually, I'm going to move fluidity up and viscosity down because fluidity is easier to understand, I think. So if something's a fluid, what's that mean? Liquid or gas. What's the property it has if it's fluid? It flows. You can pour it. So fluidity means a substance can flow. And flow just means change shape. So liquids are definitely fluid, but not as fluid as gases. How come? Because gases have a lot more freedom of movement. They have more space, so they're not bumping into each other as they're trying to flow by, and they don't have the intermolecular forces to contend with. So then viscosity is the opposite of fluidity. Fluidity is how well a substance flows. But viscosity is how slow or bad a substance flows. So air isn't even considered to be viscous. If you have air with viscosity, that's some serious pollution. You should get a respirator and get out. You don't want air that thick. So, different gases, they're all going to have the same fluidity. It doesn't matter if it's all nitrogen, all oxygen, or a mixture. But liquids vary a lot in how well they flow. So how slow or bad a substance flows, a lot of us think of it as thickness. And sometimes we want things to be viscous. Like the fluid in your eye, you don't want that too runny or it just drips out all the time. Okay, this is kind of gross, but the same thing's true of your nose. You actually want it to be a little thick. You don't want it to be too thick, but you don't want it to be too runny. So viscosity is a big deal, and actually it's a really big deal in the human body. We have all kinds of fluids that have to be the right viscosity, or else it creates problems. So liquids, what will increase or decrease the viscosity? Yeah, you can increase or decrease viscosity. The quickest one is with temperature. Colder is slower. Potentially you could do it with pressure. A substance with more intermolecular force, so a more polar substance. So that'd be more viscous or less viscous? Should be more viscous, yeah. When we say more viscous, again, we mean slower. So those are going to be the two big things that affect the viscosity. And then surface tension. Surface tension is pretty similar to density, but it's looking at the density or how tight particles are on the surface. of a liquid. So polar, well, let's just go with intermolecular force. So greater intermolecular force means higher surface tension. So when you jump into salt water, well, that's actually a different issue we'll get into. If you had a swimming pool full of rubbing alcohol, or even if it was really soapy water, that breaks the surface tension of water. When you dove into the pool, guess what would happen? You'd go crashing right down to the bottom. Probably break your ankles or crack your head, whichever way you're facing. Because the water's not going to slow you down. The surface tension's not going to slow you down.